Okay. All right, let's get going because, all right, quiet please. So I was a little behind last time, so I want to make sure I get through a few things. So we're going to do a quick news article here. Basically, it's an article that came out in the New York Times, I believe today, basically just saying that surprisingly the growth in capacity of data centers in the world is growing. Data centers don't realize that there's a recession. So there's no global downturn if you're in the data center business. And frankly, if you look in Soda Hall and you see the list of companies that are trying to recruit computer science people, you realize that there's not really much of a global slowdown at all in the computer industry as a whole. Do you have your clicker? Oh, thank you, man. Oh, good. So one thing, that picture, if you look at the article, it's very cool. That's Google's latest data center. It's built way up in the north in Finland, where you don't have to pay much extra for cooling, and that's what people are doing with data centers. Okay, so what I want to do today is really I want to wrap up the cache discussion, and then on Friday we'll be back with Dan. We'll have some videos, more jokes. He'll talk faster than I do. You guys it'll be better, believe me. So we're going to do that starting on Friday. And then, of course, this is the final sprint to the midterm, so we'll talk about that too. All right, so quick review of direct map caches, and then we're going to wrap up. We're going to talk about performance, some ways to make performance better, and then we'll wrap everything up. So, okay, so I showed this picture last time, and it was I had tried to improve it, and that was probably a bad idea. So let me just show you this picture again. So what this picture is, so remember, direct map cache, okay? So that means that any given address in memory can live in exactly one entry in your cache, okay? That's what direct map means. And we're going to see something different than that in a little bit later. So this cache has 256 entries, but it's a little different than what we had seen in the first cache we looked at, in that here, the data in each entry is made up of multiple words. Okay, so in this example, there's 4 words per block. Okay, so now when you get an address, remember we have the tag, we have the tag, the index, and the offset. Here our offset gets split into 2 pieces, and this is the thing I tried to simplify last time, which was not a good idea to simplify. So because our unit that we deal with is a word, words are 4 bytes. So we still use the 2 least significant bits to tell you which byte of the word you're interested in. Okay, but you always go to the cache and get an entire word. Okay, but now our problem is before we could go to the cache when we went to an entry, there was only 1 word there. But now, because we're trying to take advantage of spatial locality, we've got 4 words in each entry. Okay, so when you go to the entry, you got to not only find out, is what you're looking for there, but if the piece of memory you're looking for is there, you got to figure out which word in that 4-word chunk is the one that you want. So what we're going to do then is we're going to use our index bits to find out which entry, right? That's what we always do. And then once we know which entry, then we're going to do 2 things. We're going to use our tag to say, okay, is the thing that's sitting in this entry right now the thing I'm looking for, right? So do the tag bits in the cache entry match the tag bits of my address? Okay, if yes, that's good. You also want to check to see if the valid bit is set, of course, otherwise you're looking at garbage. So if both those are true, that's a hit. And then you're only interested in one of these 4 words. So we're going to use these 2 bits. So the least order 2 bits are used for the byte. The next 2 bits tell you which of the 4 words in that cache entry are the one that you're looking for, the one that address is pointing to. So you take those 2 bits, you feed that into this multiplexer here. That's going to select one of these 4 words, and those 32 bits for that word are going to pop out the top. Okay? So 2 things I want you to remember about this picture. One is just the way a direct map cache works, where for any given address, there's only one place it's going to be in the cache if it's there. Okay, and you check to see if what's there is what you're looking for by using the tag bits. And then the second thing is, in order to take advantage of spatial locality, like we talked about last time, you might want to put more than one word in your cache entry. And if you do that, you need more offset bits to find the word that you're looking for. All right? So that's review. Any questions about that before I move on? All right, cool. I will not change slides before lecture again. That was my promise. Okay, so now let's talk about performance. Okay? Because that was actually what I wanted to do last time when I showed you the metrics for Moneyball, right? Why performance is important. Okay, so let's take a big step back and think about how do we think about performance in a computing system, okay? So computers have this thing called a clock, right? Processors have a clock, and that clock ticks at a regular interval, and that's the thing that determines how fast things are going to happen. That's what determines how fast things are going to happen inside the processor, okay? So each tick of the clock is called a clock cycle, okay, and that's some unit of time, a very small unit of time. And the clock rate, or the clock frequency, basically says how many times that clock ticks per second. Okay, so if you read about a processor, you're thinking of buying a machine, and it says, this has a 3 gigahertz processor, okay, that's telling you how fast that clock is ticking, okay, in that processor. And it's ticking at 3 gigahertz a second. And what that means is it's ticking 3 billion times a second. Okay? So the clock rate tells you how many ticks there are per second. The time it takes for a single tick is just the inverse of that. Okay, so if you have a 3 gigahertz CPU, what that means is each tick is 333 picoseconds. Okay, or a third of a nanosecond. Okay? So now when you go out shopping for, and you decide, do I want to spend an extra $500 to go from, 3 gigahertz to 3.2 gigahertz? Well, you can calculate how many picoseconds you're going to save for that $500 and decide if that's worth it. Okay, picosecond goes by pretty quickly. All right, so that's clock speed, okay? Now, if we're only interested in kind of how fast that CPU was ticking would be done, but we're not, right? That's not really very interesting. When you're trying to make the decision, should I go with the 3 gigahertz machine or should I go with the 3.2 gigahertz machine, you'd really like to know what that means for you when you're running a program, right? Because that's really what you care about. You don't actually care how fast the CPU is ticking. So we want to really think about how fast we can run instructions, okay? And in particular, the time it's going to take to run a program, so how many seconds per program, okay, that depends on the product of 3 things, okay? First of all, how many instructions are there in the program? And these are instructions at the machine level. So this is after you've taken your C, you've compiled it into assembler, that assembler has been translated into machine code. It's how many of those instructions are there, okay? Actually, let me go through this way. At the end of this thing is just the cycle time. Okay, that's how long a clock tick takes. Okay, so you know how many instructions there are in your program. You know how long a clock tick takes. Then all you need to know is this thing called CPI, okay, which is the clock cycles per instruction, so clocks per instruction, okay? So basically, the amount of time that your program is going to take is the number of instructions you have times the average number of ticks that go by for each instruction, that's CPI, times the length of a tick, okay? So when we put all that together, then we can figure out how fast a machine is going to be for running our program. Okay? All right, good. So what does this have to do with caches? Oh, okay, one other thing. We'll talk about CPI in a bit, but you might be interested to know, okay, when would you have a CPI of 1? So one clock cycle, one instruction happens in one clock cycle. Actually, Dan's already talked about this. There are certain operations like add and, add immediate and those kind of boring operations. Those happen in a single clock cycle. Okay, so that's for that's CPI 1. When might you have a CPI greater than 1? What kind of instruction might take longer than a single clock cycle to run? Yeah. Yeah, load or store, thank you. Right. You go to memory isn't that fast. Chances are that's going to add into your CPI, your average clocks per instruction. And so that's why this is relevant to caching, or why caching is relevant to to performance. Okay? So we're going to talk about what caches do to CPI. Bonus question, can CPI ever be below 1? Can you ever run instructions on average faster than 1 clock tick per instruction? Yeah. Yes, and the answer is yes. And the big idea, the great idea of computer architecture that makes that happen is parallelism, exactly. So if you can do multiple things in a clock tick, your average cycles per instruction is going to be less than 1. Okay, or at least that's going to bring down your average CPI. Okay, so it's really interesting, right? You have this idea of a clock that's ticking at this constant rate, and you say, oh boy, it must be really easy to figure out what computer performance is going to be. But it's really not, because some instructions take longer than others. Individual instructions might take a different amount of time depending on whether you have a cache hit or not, okay, or other properties, like where in memory things are located. Or if you're doing a good job of different kinds of parallelism, you can even do better than a single cycle per instruction. Okay? So you sort of have the whole gamut. So you really have to understand what's going on in the whole system in order to really understand the performance. Okay? And caches are a big part of what's going on in the system. Okay? All right. So let's start thinking a little bit about how we're going to think about performance in a memory system or in a cache system. So the first concept is this thing called average memory access time, or AMAT. Okay? And AMAT is just, when I have a memory request, let's say a load. Okay, so we're doing a read. How long is that going to take? And remember, our unit of time is a clock tick or a cycle. All right. So AMAT is pretty simple. It's basically just however long it takes. So let's say I make a request and I go to, I've got a load command. I go to the level 1 cache. And if it's there, that's a hit. That costs me a certain amount of time, okay? And in particular, we want to build our level 1 cache so that it never takes longer than a clock cycle to give us the answer. Okay, so in general, the cost of a hit to level 1 cache is going to be a clock cycle. Okay? Unfortunately, when you go to the cache, what you're looking for might not be there. Okay, so it takes you a cycle to figure out, to go to the cache and return what you're looking for. The problem is, what if it's not there? Well, then, as you know, we've got to go out and find the thing that's not in the cache. Okay, and so far, if you've just got level 1 plus memory, what that means is, you get a load command, you look in level 1 cache, if it's not there, you go to memory. Okay, well, how much is that going to cost? Well, that's the miss penalty. Okay, so that's the time it takes to go to memory. Okay, and then the question is, how often do you have to go to memory? Well, that's your miss rate. So remember when we talked about how good we were doing with the cache, we had a bunch of requests, and every time we had a hit, we said, great, that's a hit. Every time we had a miss, we said, oh, too bad, that's a miss. And then at the end, we looked and we said, hey, what was our miss rate, right? What percentage of the time did we go to the cache and not find what we were looking for? So the average memory access time is really the cost of a hit, the time of a hit, plus the percentage of times you have a miss times how long it takes you to service that miss. Okay, and that's the simple AMAT calculation. Okay, so here's an example. So let's say you've got a processor that's got a 200 picosecond clock. When you miss in the level 1 cache, you go to memory, and that costs 50 clock cycles. Okay, so think about that. 50 clock cycles. That's 50 instructions. Or if your CPI is better than 1, that's more than 50 instructions. Okay, now let's say you've got a pretty decent miss rate of only 2%. Okay, so 2% of your request to the L1 cache miss. All right, and if you hit in the cache, that's 1 clock cycle. Okay, so a hit is 1 cycle, a miss is 50 cycles, and you miss 2% of the time. Okay, so you plug that into the AMAT calculation, and what you find out is that ends up being 400. Your average memory access time is 400 picoseconds. Okay, so in general, in this particular system, loads your CPI for a load is going to be 2 on average. Okay, through that calculation. Question? CPI is dependent. Okay, so, CPI is dependent on the processor and the instruction, and whether you're doing things in parallel and whether you're finding things in the cache. Oh, great question. So that means if I see the clock speed, but I don't know anything else about the machine, does that really tell me anything? And the answer is not really. So, you can easily have a 3 gigahertz or 2 gigahertz machine if you have the caches set right and the processor's built the right way. It's going to be much faster than it's going to run your program much faster than a 3 gigahertz machine, even though that little heartbeat in the 3 gigabit machine. The 3 gigahertz machine is going faster. Okay, so that's why when you're buying your laptop or whatever, you might want to look at the processor speed, but there's a lot more going on. That's exactly the point. Okay, and part of that is the way the cache works. Yeah. Oh, okay, if we're trying to find a weighted average, why don't we multiply the time per hit by the hit rate? Because the idea is you've got to pay, so this is actually a good question too. You've got to pay the price for a hit anyway. So the price of a hit is look up in the cache and grab the data out. Okay? The cost of a miss is look up in the cache, realize it's not there, go to the next level of the hierarchy, bring it back in, and then bring the data back. So you got to do all the work you had to do for a hit plus the work for a miss. Yeah?
So in this question, if you miss, then the instruction will take 51 clock cycles to actually finish?
Well, if you, I'm sorry, in this example?
If there's a miss, then it would take 51 clock cycles to...
Oh, okay, yes. So in this example, a miss costs 51 clock cycles, a hit costs 1 clock cycle. Absolutely. Yeah. Okay, great. So then you say, okay, well, maybe what I'll do is I'll make the cache bigger. Okay, and maybe that's going to help. And, the answer is maybe it will. And so if you make the cache bigger, chances are you'll have a lower miss rate, at least up until a certain size cache. Okay, so as you can keep more in the cache, the chance of finding what you want is better. That means your chance of a miss is less, which means your miss rate goes down. But there is a negative effect, and I might have actually confused people a little bit last time. There is a slight effect that if you make the cache bigger, the time it takes to look up things in the cache can take a little longer. Okay, so because remember you've got a certain number of index bits, and if you grow the cache by adding more entries, your index has to be more bits, and it takes it slightly longer to decode those more bits. Okay, but in general, if your level 1 cache returns, if your cost of a hit in level 1 is less than or equal to a clock cycle, you're okay. All right? So this effect of a bigger cache is not really the access time cost of having a bigger cache for reasonable cache sizes isn't really a big deal. Okay? The other thing, as we talked about last time, okay. Well, anyway, there's a trade-off. There's another way you can grow the cache, but we'll just talk about that later. All right. So that's AMAT, but AMAT doesn't quite answer our question. Okay. So now let's close the loop. Okay. And now let's say, all right, how do we figure out the speed of our program when we worry about the cache hierarchy as well? Okay. And that's what this is. So CPU time is instruction count times the average CPI times the cycle time. Okay, that's the equation I showed you before. Now, what does that mean when you worry about the memory hierarchy? Well, the CPI expands into this expression, which is it's the ideal CPI. It's kind of as fast as the processor can really run, plus whatever you spend on average stalling for memory or for a miss in the cache. Okay, so basically you want to penalize the CPI by the AMAT. Okay? All right, so this is sometimes called the CPI stall. Oh, jeez, how did I do that? All right. Anything interesting there? Uh-oh, now we're really in trouble. There we go. Weird. This line is... all right, hold on a second. I want to make sure I show you my slides, not somebody else's. Okay, that was exciting. Okay, so now we need a model for memory stalls. All right, and pressing very carefully here. memory stall cycles, so the amount of time, the number of cycles we're going to wait for memory is basically how many times we access memory per instruction on average, times the miss rate, times the miss penalty. Okay? So the thing we were missing before, no pun intended, was this idea of what percentage of instructions actually access memory. Okay? So, and right now we're focusing on reads, not necessarily on writes. Writes are slightly more expensive than reads, as we talked about before. Okay, so basically, if you go back, if you look at this equation, if your processor gets faster, right? So if you get a faster clock, that's actually going to change this. Well, actually, let me do it on the slide that it was supposed to be. So if you can do a better job in CPI, and you can make that ideal CPI go down, okay, so maybe add more parallelism, and so the number of cycles per instruction goes down, then you've got to be a little careful, because that means that your memory is going to be more expensive, right? So for example, relatively speaking, here's a processor, let's say the CPI ideal is 2. Okay, so if you don't worry about memory, you basically, on average, it costs you 2 cycles to execute an instruction. Okay, this is slightly different numbers. You have a 100-cycle miss penalty. Okay, and let's say that 36% of your instructions are loads or stores. So 36% of your instructions go to the cache. Okay, they need something from memory. Okay, now, remember, we've got an instruction cache and a data cache. Typically, you do really well in the instruction cache in terms of hits because, oftentimes you're going sequentially through a program or you're in a tight loop, okay, and the instruction cache does a really nice job. So let's say your miss rate for the instruction cache is 2%. Your data cache, you have locality, so it's worth it, but maybe not as much locality. So let's say that that's a 4% miss rate. Okay, so if you do the math on that, then 2% of let me make sure I get, so 2% of all your instructions miss in the instruction cache. So you pay a penalty of 100. Okay, so every instruction there's a 2% chance that it's going to miss. If it does miss, that's 100 cycles. Okay, so that's for every instruction because those are misses out of the instruction cache. Plus, 36% of those instructions access the data cache, and 4% of those are a miss. Okay? And again, a miss costs 100. All right? So if you multiply all that out, you end up with a stall cycle of 3.44. Okay? So on average, the average instruction sees 3.44 cycles of delay because of the memory hierarchy. Okay? If you could keep everything, all your data was in level 1 cache, that number would be 0. Or maybe it'd be 1. I think it'd be, it'd be fine. It'd be 0. So, so if you think about it, your ideal CPI is 2. You're paying on every instruction a penalty of almost 3.5 because of the memory tax. Okay, so the fact that you can't fit everything in level 1 is costing you almost a factor of 2 more than sort of the native speed of the processor. Okay? So, that's a big cost. Okay, and that's why we spend a lot of time on designing the cache hierarchy and making things try to go faster. Now, if the CPI ideal goes down to 1, okay, so let's say you do some tricks with parallelism and get that CPI down, the system's going to run faster, but as a percentage, this memory cost is a higher percentage. Right? So now the cost of memory for every instruction is more than 3 what the cost of the CPU is. Okay? So, as processor gets faster, it becomes more and more important to do a better job of managing your memory. Okay, that's the main lesson there. Okay? And that's why as processors have been getting faster, there's been more and more cache put on them. Okay? And then, some other questions you can deal with later. So, okay, so given that if we're not careful, it's very easy for the memory portion of what we do to outweigh the actual processing portion of what we do, we want to be really, really smart about how we handle memory. So let's try to be a little smarter. Okay? So we've got our CPU. We've got our level 1 cache, right? That's our cute little abbreviation for cache, the $sign. So what we're going to do, the way we talked about it before was, you look, the CPU goes to level 1. If it's not in level 1, you go out to memory. Okay? And go to memory was, a horrible expense, 50, 100 cycles, right? So 100 times slower than the processor runs. Okay? So it's really slow. So what if we said, okay, rather than just having that very stark reality of if it's not in level 1, it's in memory, what if we try to take advantage of a little more real estate on our chip and put some more cache in there? So that comes up with the idea then of a level 2 cache. And so now what we're going to do is if we have a request, we go to the level 1 cache. If it's in there, that's a hit we return. If it's not in there, that's a miss. And instead of going to memory, we look it up in the level 2 cache. Okay, and level 2 cache works very much like the level 1 cache. It's just going to be a lot bigger and a little further away. Okay? So great, if it's in the level 2 cache, that's a hit. We bring it back into the level 1 cache, and we return it to the CPU. Okay? So again, temporal locality says if we access that thing, we're probably going to access it again soon. So we put it in the level 1 cache as well as returning it to the CPU, so that when the CPU asks for it the next time, it's in level 1. Okay? If when you go to level 2 it's a miss, all right, well then we're going to go to memory. Okay? And when we go to memory, we're going to bring it into level 2 because of temporal locality. We're going to bring it into level 1 because of temporal locality, and we're going to give it to the CPU. Okay? So basically, the requests go from the highest part of the hierarchy down to the lowest part, and the data flows back up from, it gets put in the next higher level, the next higher level, the level 1, and given to the CPU. Okay? Yeah? Okay, that's a really good question. So if I built the world's worst caching system, and I didn't have temporal locality, and I didn't have spatial locality, would I be better off just going straight to memory? And I think the answer is yes, but the chance of you being able to build such a bad cache is virtually zero. And it's because you're going to get, even just think about the instruction cache. You're here, you go to the next instruction, you go in the next instruction, you're in a loop, you go back to the top. You can't avoid that. Even if you wanted to, it's hard to avoid that. So the answer is yes, the cache, and it's a really good point. The cache certainly adds complexity. I'll show you actually in a second some measure of what it adds. But it pays off tremendously. Okay, so let's talk about these multiple levels. So typically, level 1 is on the same chip as the processors. I'll show you a picture in a second. Level 2 is often on the same chip nowadays, and even level 3 is on the same chip. And one difference is that level 1, you typically have an instruction cache and a data cache, and level 2 is typically what's called a unified cache, meaning all the memory requests, whether they're for instructions or for data, go to that cache. Okay? And level 3 is also unified. Okay, so now in this so it's a pretty simple concept, I hope, because we've been talking about memory hierarchies for a while now. But you have to redo your AMAT calculation, right? So now, instead of it being just the L1 hit times the cost of an L1, plus the L1 miss rate times the cost of a miss, it gets a little more complicated in that the cost of an L1 miss depends on how long it takes you to get a hit in the level 2, plus your miss rate at level 2 times how much it costs you when you miss in level 2. Okay? And if you can imagine, if you have a level 3, well, the miss penalty of level 3 is the cost of a hit in level, the miss penalty at level 2 is the cost of a hit in level 3, and so on. Right? So you could just stack these things up to calculate your AMAT in one of these multi-level caches. Okay? So let's look at a new example. So we've got two-level cache. Cost of a hit in level 1 costs you 1 cycle. Okay, 2% miss rate. Cost of a hit in level 2 costs you 5 clock cycles, 5% miss rate. Okay, because remember, as you get further from the processor, you know, your locality, you're already at the top of the heap. You're really taking advantage of most of the locality. So as you go away from there, you're sort of getting that next level of locality. It starts to be like secondary effects. So even though the L2 cache is bigger, chances are, because you have less locality for the requests that don't get satisfied by level 1, chances are your hit rate's going to be worse than level 1, even though it's a bigger cache. Okay? So let's say you have this set up. Let's say to get to main memory, it costs 100 clock cycles. Okay? So 1 cycle for L1, 5 cycles for L2, 100 cycles for memory. Okay? If you didn't have an L2 cache, then our AMAT is the cost of a hit times 2% times the cost of going to memory. So that's 3. That's the cost of 3 cycles average memory access time. If you have this L2 cache, it's a miracle. Okay? It's the cost of a hit in level 1 times the 2% of the times you miss in level 1 times the cost of a miss in level 1. Well, what's that? That's the cost of a hit at level 2 plus the miss rate at level 2 times the cost of getting it out of memory. Because if it ain't in level 2, you go to memory. That, just by adding that level 2 cache, you go down from an AMAT of 3 to an AMAT of 1.2. And if your CPI ideal is something like 1, that's a huge difference, right? That's a tremendous speed up in the speed of your program. Okay, so that's why people build systems with multiple levels of cache. So this picture isn't in your handout, and I'll tell you why in a second. The picture in your handout actually came from the book, and it turns out it's wrong. And I verified this with one of the co-authors of the book who sits next to me. So he gave me this picture instead. So this is the Nehalem processor, which is not anymore the latest, greatest Intel processor, but it's pretty good. If you buy an expensive server with Intel chips, you'll have these in it, chances are. Okay? So that's the die. That's what the chip looks like. What's going on in there? Okay, well, you got cores. Okay, so each core is a processing unit. We're going to talk about that later, not really today. But the Nehalem has 4 cores. So if you look at all that stuff that's going on there, you'll see you've got 4 cores. Interestingly, 2 of them are kind of facing this way, and 2 of them are facing the other way. If you look at what's going on in the transistors there. Okay, but what do we care about that? Well, we don't yet. But what we care about is this. It's this whole space, all these transistors, all this real estate on that chip is L3 cache. Okay? So we're not just talking in this class about some sort of theoretical construction. You know, that's if you pop the top off of your processor chip, which I strongly recommend you don't do, that's what you'd see. Okay, so that's level 3. Okay, what happened to level 2 and level 1? And this is where this picture differs from what's in the book. There's some other stuff like memory, and we'll worry about that later. Okay, let's look at one of those cores. So now we're zooming in on one of those cores. Okay, what's going on there? Well, we've got a bunch of real estate we're going to use for our execution units. And oh, look at that. There's the level 1 instruction cache. Okay? And there's the level 1 data cache. Okay, and I said to Professor Pattison, how do you know that that's where they are? And he said, well, somebody at Intel told me that's what they were. So, you know, this might be totally wrong. It may be, you know, no better than what's in the book. But in the book, the one that's in your handout, it shows level 2 being shared, and it's not. Level 2 is sitting in that core. So, you know, basically, your processor's zipping away. When it needs to go to memory, it says, hey, you got any data for me in level 1? If it does, it returns right away. If it doesn't, you go all the way to level 2, right? If it does, you return. If it's not in level 2, you go all the way to the shared level 3, okay? And then you return. If it ain't in level 3, you know, take a coffee break, right? You're going all the way out to memory, and then you got to come all the way back. Okay? So this stuff is real. It's in, you know, you're doing your Facebook page right now. You're doing your Facebook page because of that. And that's why it's running fast. And I know you're not doing your Facebook page. I'm just joking. Okay. So, yeah, quick question. Yes. So level 1 is split typically into 2 caches, one for instruction, one for data. The reason that is that the instruction access pattern is so different than the data pattern that you can get a lot of benefit by separating them. A couple more quick questions. Yeah. Yeah, see, this is the part, I'm with you. Why would you put the instruction one over there? I don't know. I really don't know. Well, I'll try to ask again. Okay? But I agree. I looked at this and I'm like, well, if I was building this thing, I'd put the instructions right there. But, okay. So this might be off by, but you get the, think of it as an artist's representation. Yeah. What does the rest of the chip do? I purposely took that out so that people wouldn't ask me about it. So you'll see this picture again towards the end of the semester, and it'll have all the rest of it filled in. But basically, it's doing branch prediction, it's doing some math, it's doing a bunch of stuff. It's playing around with addresses, it's doing virtual memory, it's doing a lot of stuff. Okay, do you have something you want to? Okay. Oh, okay, good. Yeah, thank you. So the controller is kind of over here, and that's why the instructions are over there. So we'll see it later. Okay, so Professor Garcia thinks that this is actually okay. And I'm fine either way. Okay. All right. Because no matter what, these things are they're that big, right? I mean, how much could it possibly matter? No, it matters a lot, actually. It matters a lot. It really matters a lot. If you're a database guy like me, it hardly matters. But if you're designing processors, it matters a lot. Okay, so why might you miss from a cache? This is in the book. And there's the 3 C's of cache misses. There's compulsory misses, which are, when you fire up your machine, you start your process, all the valid bits in the cache are set to 0. So the first access to an item, there's no way it's going to be in the cache. And then even, the first time a program ever accesses an item or an address, that's going to be a miss, unless you brought it in bigger. So let's stick with the valid bit thing. So, when you start up with an empty cache, you're going to miss until the cache fills up. Okay, that's a compulsory miss. Capacity miss is what we've been talking about, which is, the L1 cache is this big, the L2 cache is this big, the L3 cache is this big, memory's that big, and disk is, much, much bigger than that, 100 times or 1,000 times bigger than that. So you just can't fit everything. That's called a capacity miss. Okay, so the thing you want just isn't there because it didn't fit. And the one that's the trickiest is this thing called a conflict miss. Okay? And that is, if you remember, when in our direct map cache, when we look at a cache entry, we check the tags and see, is this thing at the entry the thing at the address that I'm looking for? Is it representing the memory of the address I'm looking for? And if the tags don't match, then that means there's something in the cache entry, but it's not what you're looking for. Okay? That's called a conflict. Okay? Because when you read something into that cache entry, it overwrites something or it kicks something out. Okay? It may be that you really wanted to use both those two things at the same time, but unfortunately in the direct map cache, they have to end up in the same place. That's called a conflict miss. Okay? So if you want to speed up your cache, what can you do? Compulsory, you're stuck. Okay? Unless you sort of could come up with a clever way of preloading it. Okay? Capacity, you can solve that by, to some degree, making the cache bigger, but there's a limit to how much that's going to do. And then the third thing you can do to speed things up is to try to remove these conflicts. Right? So try to minimize the amount of time I get into trouble because two things I want near each other happen to map to the same place in the cache, so I can only keep one of them. Okay, and that's what we're going to talk about next. Okay, so we talked about direct map cache. The alternative is something that's called a fully associative cache. So direct map cache says, given an address, I look at the index bits, and that tells me the one exact place in the cache that thing could be. Okay? Fully associative is total opposite. It says, that address can be anywhere in the cache. Okay? That's fully associative, so there's no restrictions. Now, there's a middle ground, which actually turns out to be the best of both worlds, which is what's called a set associative cache. And in fact, it's called an n-way set associative cache, where n-way says how many things are there in the set. So in a set associative cache, any given address, instead of mapping to a particular one single block in the cache, maps into a set of blocks. Okay? And n-way says how many blocks there are in that set. Okay, so I'm going to show you an example. Don't worry. Okay, so just pictorially, direct map cache, if I'm looking for this particular page, the only place it could possibly be is in this entry, right? And in a set associative cache, and this is a two-way set associative cache, my entries are effectively two blocks, or two ways, they call them. Okay? So anything that maps to set 0 could either be in this entry or this entry. Anything that maps to 1 can be either to this entry or that entry. And fully associative doesn't even have that restriction. That item, that address might show up anywhere in the cache. Okay? So if you think about it, block associative is relatively, direct associative is direct block is very easy because you just look up the index, boom, go into the cache. If it's there, great. If it's not, you got to get it. Associative, you kind of got to poke around a little bit. You got to look to see, it could be in multiple places. So you got to hunt around a little bit. Okay, so let's look at why you might want to do this. So this is a direct map cache, and it's just a simple access pattern. We access address 0, then address 4, then address 0, and address 4. Okay? And basically, if 0 and 4 map into the same cache entry because of our direct cache, well, you read in 0, that's a miss. Then you go to get 4, well, 0's in there. You check, oh, no, I need the thing with tag 1, but what's in there has a tag 0. So, oh, that's a miss. So I bring in 4. Now I access 0 again. What's in there has tag 1. That's not what I'm looking for. What I'm looking for has tag 0. So I have to read that in. And it just goes on and on. So here, you're getting exactly, this is your case. This is, you've done all this work to build a cache, and you're getting absolutely no benefit out of it. And you're paying the price of all that real estate. Okay? Yeah, quick question?
So direct mapping is the simplest.
Direct, yeah.
So why don't we just optimize the compiler to work best with that?
Well, okay, so direct mapping, the question is that direct mapping is the simplest one, so why don't we optimize the compiler to work with that? It's an interesting question, but sometimes it's out of the compiler's control. The problem with the direct mapping is, given an address, it can only go to one place. And you could think of clever compiler tricks to try to, do the right stride of your instructions and all that so that things would work. But once you get to data, that's also totally out of your control. So there's a lot of reasons why it's hard to so it's interesting to think about being smart like that, but it's hard to do. Yeah. Yeah. Yeah, the cache logic is all done by hardware. Right, all these lookups and everything. All right, so let's look at this. So let's solve that problem. Let's do an associative cache. So we want to move from a world, we'll do two-way first, because that's easier. So we want to move from a world where any cache, any address can only end up in one entry in the cache to where it can be in two. That's a two-way associative cache. So basically, this block, this first address, can end up in either entry 0 or entry 1. Okay? This green block can end up here in set 1 in either entry 2 or entry 3. Okay? So that's your cache. So before you could only go to one place, now you get to go to two. And so how are we going to do that? Well, again, we're going to play with the interpretation of the address. So, if we have entries that are a word in length, okay, so we need 2 bits at the end to say which byte we're interested in. So we're not going to, that's our byte offset, okay? Then we have 2 sets in this cache, because it's a cache of 4 entries. It's a two-way associative cache, so you have 2 entries of 2 lines each, okay? So what that means is we need another bit. We need the next bit to tell us which set is it in. Is it in set 0 or set 1? Okay, so the index here becomes, basically becomes 1 bit, okay? Now you'll notice if we have an address that tells us we belong in set 0, it actually doesn't tell us which one of these it's in. We have to actually look to see if it's in one of those. It could be in either one or none of them, okay? So we're going to use that next order lower bit to figure out which set we go into, and then the rest of the bits, as usual, are going to be the tag, okay? So given an address, we ignore the first 2 bits because that tells us about the byte, and we're only interested in words right now. The next bit tells us if we're in set 0 or set 1, and the rest of the bits are the tag. And given the set that we have to go to, we match to see, hey, is tag 000 in there? Is tag 000 in there? If it's not, it's a miss. Okay, if it's in one of them, then it's a hit. Okay? So that's two-way set associative. So now let's do our example again, 040404. Same size cache as before, except instead of treating it as a direct cache with 4 cache entries, we're going to do it as a two-way set associative cache with 2 sets of 2 ways or 2 entries each. Okay? So now we'll do that. So we read 0. 0 belongs in set 0. It's not there, we miss it, we bring it in. Great. Now we read 4. 4, if you do the math, belongs in set 0. So we look in the cache, it's not there, but that's okay. We go out and get it. We still have room, and we bring it in there. Okay? So remember, in the direct cache, we had to kick out page 0. our address 0 and replace it with 4. Here, we have the flexibility because there's a two-way set. So as long as there's room in one of them, we can use it. Okay, great. Now what happens? Ask for 0, it's a hit. Ask for 4, it's a hit. And if you keep doing it, we get a perfect hit rate after the first two compulsory misses. Okay? So we've basically solved the conflict case. Okay? And that's really all set associative caches are about. So we went from a hit rate of 0 with the same access pattern and the same cache size. Now we have a hit rate of 75%. Okay? I want to make sure I get through a couple slides, so let me go. Ask me a question after if you want. Okay, so we solved that problem. What's this picture look like for the set associative cache? Okay, well, here's a 4-way set associative cache. Okay? It's got 256 sets of 4 data entries each. Okay? So what do? All right, well, each entry stores a word, so we need those last 2 bits, or the least significant 2 bits, as a byte offset. Okay? Our index, because there's 256 of these guys, is 8 bits. So we use those 8 bits to tell us which set we need to look in. Okay? And now, because it's a 4-way cache, I previously showed you 2-way, now we'll do a 4-way. So it's a 4-way, there's 4 possible ways, I don't know who made up this terminology, there's 4 possible places that thing might be. And so what you do is you actually check all 4 of those tags, and again, you're right, this is done in hardware, but it takes time. Okay? So you check all 4 of those tags, and you see if any of them match. Now, at most, one of them will. Okay? You also have to check the valid bits, as always. Okay? And if one matches, this is an OR. Okay? Oh, boy. If one of them matches, that's a hit. If 0 of them match, that's a miss. So if one of them matches, that's a hit. And then this is a multiplexer. You feed all 4 of these words into it, and the one that's selected by the 1 bit here is the one that gets returned. So one of those 4, if there's a hit, one of the 4 will get returned. If there isn't a hit, that's a miss, and you've got to go out and find what you're looking for. Okay? Now, okay, and I'm going to skip this. This is in your notes, but this basically just shows you what happens to the address as you increase the associativity. Basically, as you increase the associativity, your index gets smaller, your tags get bigger. Okay. All right. So when you have a hit, that's how it works. What happens on a miss? On a miss, you've got a decision to make. You've got to decide what to throw away. Okay, and you have a couple choices. We'll talk about 2. One is you pick a random thing to throw away. The other is you say, I'm going to take the one that I used the longest ago and throw that one away. Can anyone say why that might be a good thing to do? That's called least recently used. Yeah. Yeah, temporal locality tells me the thing that I used the longest ago is probably the least likely thing that I'm going to use next. Okay? All right. So how do you implement least recently used? Dan's getting nervous because he has to go to another class, so I actually will finish close on time. It's pretty simple. If you have a 2-way set associative cache, you basically, you're excused if you need to go. If you have a 2-way set associative cache, you need 1 extra bit, okay? And then when you access something in the cache, you set that bit to 1, you set the other bit to 0. Okay? That always tells you the one with the bit set is the one of the 2 that you referenced more recently. That's easy. If you have more than 2-way associative, then you have to play a trick basically where you sort of approximate it. And you basically have a pointer that says, hey, here's the next thing I'm going to replace. If you hit something, you set the bit, and then you move the pointer to something else. Otherwise, you just replace it. And that ends up being a coarse approximation to least recently used. Okay. So in your notes and in the notes we'll post, we're going to talk about, it just shows you how particular caches are organized according to the things we've talked about. So just to wrap this up, we talked about the performance, how you measure the cache performance, how that impacts the actual performance of programs. And then we talked about 2 tricks for making things work better, multi-level and set associativity. And with that, I will let you move.